Class is in session. Welcome back to General Statistics. Today we will discuss the expected value and standard error and look at the calculations of these values. And the expected value and standard error are both concepts that we will use throughout the rest of the course. It's no exaggeration to say that some of the things, the calculations and ideas that are presented in this chapter and the next will, everything else we do in the course will depend on them in some ways. So we're going to focus in chapter 17 on getting a good understanding of the calculations and the structure of these concepts, and then in 18 we'll break them down more theoretically. There we go. The expected value is related to the idea of a chance process. So you have to, in order to conceptualize an expected value, step back and remember that we're talking about, for one, a chance process that's not just running one time, or we're not just looking at the probability of getting heads or tails on one toss of a coin or maybe across a couple of tosses. We're now talking about running our chance process repeatedly, and we will break this down into in a lot more detail, this idea of the repetitions and number of trials. It really translates in many, many ways onto what we are going to do in the next unit of the course as well. So this is very closely linked up. So we know that the sum of draws from a box will be around its expected value, but they're going to be off a little bit. The amount that the values are off is similar in size to the standard error, which we'll figure out how to compute in a minute. And the formulas for the expected value and the standard error both depend on the chance process that generates the numbers. And it depends on the chance process in a few different ways: the number of trials, the range of the specific numbers in your set or in the box. So there's a few different ways that your values link back logically to the actual numerical values, the number of trials, or the categorizations that you've used. So the formula for the expected value does have it's a shortcut to predicting how what are expected. In this case, we're still talking about sums. Sum of numbers in the box or the average numbers in the box. So you need to know your number of draws and the average of the actual numbers in the box. And these are things that are easy to get. So I'm not going to, we've already covered finding a sum or finding an average. And when you're finding the average of the numbers of the box, you're just taking the box and getting the average of the numbers in that list. We'll break down this idea more in a minute. So to find the expected value, we've got, say, 100 draws from the box with replacement. And this is crucial because with replacement, that means each time we go in, we have, each time we draw a 1, another one comes in. So there's always the same probability of getting any of these numbers individually. So to get the expected value for the sum of the draws, we need to know that the number of draws and the average of the box. So to get the average of the box, you can see that's easy. And in this case, this box has an average of 2. So then our expected value is going to be equal to the number of draws, 100 draws times the average 2. So 200 is the expected value for 100 draws from this box. Note how the expected value is dependent on the number of draws. And you can estimate your expected value based on the frequency of the numbers in the box. So we would expect these to show up in the same probabilities that they are in the box, as in the 3 or 3/4 of these numbers are 1s, 1/4 are 5s. That's how I got this 25 times 5 and 75 times 1. And we're going to skip those. So we can get the expected value of the box pretty easily, but we really need to know how much the chance error is expected to be for the box. This is a crucial issue because remember that our expected value is linked up with the idea that we're running a chance process over and over and over again. And when you are running a chance process over and over again, you need to account for the chance error. And when we're looking at the standard error, one really crucial thing to keep in mind is that we can only ever estimate the amount. This is the amount of expected error. It's not possible for us to know exactly what the chance error is in our sample. We can just estimate what we would expect it to be based on the number of trials, the size of the box, etc. And so this is a really crucial idea because as we move into our next unit, we're going to look at ways where we can determine whether or not the observed values we get from trials are within the range that we would consider acceptable, like that this is chance would predict the values would fall in this range, or if our values are outside of that range and lead us to conclude that there is a difference between our groups. So this is the major topic of our last unit, and a very important idea in statistics. And all of those calculations will go back to, in one way or another, the standard error. And you can see that now at this point we're talking about the sum of the tickets from a box. Later we'll transition to thinking about averages, but an average is mathematically linked, it's similar enough to a sum so that we can apply these rules across the topic. And so the sum of any set of draws is going to be equal to our expected value based on the probabilities of the distribution of available scores in the box, and the chance error that we will estimate using the standard error. When we estimate the standard error, we use the square root law. The square root law tells us that when we're drawing at random with replacement from a box of numbered tickets, the standard error for the sum of draws is equal to, here we have the square root of the number of draws. This is the really essential part here, times the standard deviation of the box. Now, if you're thinking, how do we get the standard deviation of the box? The same way we always got a standard deviation. And I've included a worked example later on, but we can remember doing the standard deviation in our first unit. And you just sorry, I'm juggling some of my technology over here. Okay. So the square root law is it is no exaggeration to say that the statistical procedures in the rest of our course depend on this formula and this idea that that underlies how the square root law works. Essentially, as the number of draws goes up, the sum gets harder and harder to predict. And so does the chance error gets bigger and bigger, and so does the standard error. But while the absolute value of the error goes up, the absolute value keeps increasing, the standard error goes up much more slowly by a factor that's equal to the square root of the number of draws. So if you have 100 draws, your standard error only goes up by a factor of 10 because the square root of 100 is 10. And let's think a little bit about the two ingredients in this formula. The standard deviation is distinct from the standard error. It measures the spread among the numbers in the box. There's a lot of spread in the box. The standard deviation is big, and that makes it hard to predict accurately. If the standard error, and it makes the standard error big too. The chance error is the standard error. That's what the standard error is. We'll talk about it more, but in short, when we are talking about getting the standard error for the sum of draws, what we are that is the standard error is how we quantify chance error. And so when we have say we have a smaller standard deviation, that means there's less spread in the list of numbers in a box, and we'll be able to predict more accurately or have a better predictions for the standard error using our standard error predictions for the sum of draws from the box. So let's see. And we're going to unpack these both in more details in a minute. But it's important to remember that the standard deviation is just for a list of numbers. So when you're looking at finding, it always does this. There we go. So when you're looking at finding the standard deviation for a list, you're just using the list of numbers provided, the list of data, and you apply the standard deviation formula, which was the sum of x minus x bar squared over n. Remember, n was our number of participants, the number of draws, the number of trials. N is really important in all of the calculations and all of the procedures we do for the rest of the class. We started out this course talking about how we have to always account for the number of people available in a sample because this is a major theme. And the standard deviation is distinct from the standard error because the standard deviation is just telling us the spread in the lists of numbers. It's just saying, okay, this is the spread we expect. But the standard error applies to chance variability. Now we're talking about in the sum of the draws for a chance process that's done repeatedly. And so the standard error is going to be very useful across a wide variety of statistical and a wide variety of research scenarios. So we have a little example. The sum of 25 draws made at random with replacement from the box, this box here. And in this, the average of this box is 3. And these are our deviations from average, because remember our standard deviation formula is oops, and I forgot to put my, oh, geez. Sorry about that. I hit something. And I did. This is technically what I wrote here was almost right. That without the square root, it's the variance, which is just a intricately linked to the standard deviation. Why does that keep disappearing? So you can see that the formula here worked out over here. Each deviation is squared and then they're summed. And I'm sorry, I don't know what the problem is on the writing today. But you can see we end up with a standard deviation for this box that's equal to 2. If we want to find the error, the standard error for this 25 draws made at random from this box, then we're already equipped to do it, because remember our standard error is equal to the square root of number of draws times the standard deviation. And this probably already looks kind of familiar to you because it's similar to a root mean square error term that we used in regression. So if we wanted to find a standard error for this box, 25 draws, we would take a square root of 25 times 2. So square root of 25 is 5 times 2 is 10. When we are conceptualizing using the standard error, even though it is distinct from the standard deviation, it has some nice similarities in terms of application and function. So just as we saw in regression that 68% of the distribution was within one error term above and below the curve, and in chapter 5, we saw that 68% of the population is above or below one standard deviation or one standard unit from the mean. We're still using standard units when we talk about the standard error. And for theoretical ideas and logical ideas, we'll unpack more fully in chapter 18. When we take a high number of trials, the more trials we get, the more and more the distribution of sums will resemble a normal distribution. And a normal curve allows us to relate our problem, our scores in any problem to standard units, and then use that to find the probability. So in this case, what percentage of the observed values should be between 50 and 100? we start out thinking that, seeing how there's a particular sum. The sum is just a possible value. And then we're asked, okay, what percentage of observed values should be between 50 and 100 in this range outlined here. Given that the sum is going to draws from a box is always going to have some chance variability. The chance variability is embedded, it's in the process itself. It's a random process, drawing tickets from a box, flipping coins, sampling from a population, randomly sampling. These are all random processes. And so just as a clarification, the error, that chance error, it's not part of the measurement, it's part of the random process, which is why we can use these mathematics to estimate it and account for it in reliable ways. Why are they using 6? There's 5 numbers. They didn't say the numbers here have to be from 1 to 5. The numbers in a box don't have to be sequential. They could be any numbers. They don't have to be sequential numbers. Is that what you mean? To get the 1, 2. Oh, I see. You're looking in the book. And so first we have to convert to standard units. So do we remember how to get our standard error? Or get our expected value of the box. Remember, you need to get the average of the box and divide by the number of tickets in the box, right? Number of draws times the average of the box. So this is still the same computer program that we're looking at 25 draws made at random. This is a continuation of the earlier box paradigm. So there's 25 draws from this box. First, we can find the average of the box. And that's going to be equal to the sum of these scores divided by 5. And we can get those. They'll be the mean of this box is 3, as per before. And if we want to get the expected value, we can just take our number of draws times the average of the box. But that's just the expected value. It's not the whole range of scores. So why do they have 0 to 150 as the range for the scores? Because that's the actual range. So the scores, you could do 25 draws and get 0 on each draw. If you did 25 draws and you got 0 each time, then that's the bottom of the range. It's 0. But if you did 25 draws times 6, that's the highest value you could possibly get across 25 draws from this box. And so that's where the 150 comes from. You can see that the expected value is right in the middle of the range. We're getting there, but the 2.5 is a standard unit. That's where it comes from. When you convert these mean to a standard deviation, it's a whole process here. So the range goes from 0 to 150. And if we want to convert these to standard units, remember we need to get the standard deviation. So we can get the standard deviation of this box. And didn't we already get the standard deviation of the box? Yes, it was 2, right? So we have all the information we need to convert to standard units whatever we want to convert, but let's note that what we want to get is the percentage of scores between 50 and 100. So we need to know what the standard scores that represent each of these points, 50 and 100. So this is just what we did in chapter 5, the exact same process. Wherein, and just a minute, I'm going to need a little more space. So remember that the z-score is equal to x minus x bar over the standard deviation. We can do this formula backward. We can algebraically manipulate this. There we go. So we can algebraically manipulate this equation so that we can find the z-score. We can go from a z-score to a raw score, however we want. But luckily this time we're just going forward, as in we just want to find the z-score for the values 50 and 100. So 50 minus 75 divided by the standard units 2. So that's negative 25 divided by, we divide by the standard error here because we're doing this across draws. That was, I hate it when they do that. It's kind of a pain not being able to erase because oh, there we go. So we have, because we're looking at the standard units across the number of draws, we use the standard error instead of the standard deviation here, but we already know the standard error is 10. from our previous problem, the previous calculations on this. And oops. No. Negative 25 divided by 10 is equals our 2.5 you were interested in. This one is the negative 2.5. You can see that if we did this, if we did 100, we would take 100 minus 75. We'd end up with 25 over 10, and that gives us a positive 2.5. And so you, just as a point of interest, you will definitely want to be ready on the next exam to do these Z calculations again. This is a case where the material is very cumulative. I know this unit doesn't depart directly from our last unit, but it does rely really heavily on the stuff we learned in the first unit. So, and to do the final step of this process here, we just, you can see we have our Z-scores plotted here, and we can just look up the Z-scores on the Z table. If we get the mean to Z proportion here, we'll see that it's approximately, 49.5 or some percent. And that's 49.5% for this side, because that's the mean to Z area, and 49.5% on the other side, for a total of 99%. So there's a 99% chance that the observed values will be between 50 and 100. Let's just step back to our previous, to the overall diagram here of the range, and note that if 99% of the scores are expected to be within 2.5 standard deviations, that means that while these extreme scores could occur, and they do occur sometimes, we could figure out the exact probability of any of these scores, but we'll hold off on that for another day. They're highly infrequent, and this is where we're going with our next unit, is, okay, how far does a score have to be for us to say that it's statistically, that sample is different for some reason? We get a little shortcut to use to find the standard deviation. It's a little tricky at first, but we'll be able to get the hang of it, and we'll practice this in the review exercises. But generally, this is just a shortcut for when you have a list that has only two different numbers, big and small. And you might be thinking, well, how common is that really? Well, it actually more common than you might think, given that a lot of times when we do surveys, we might have a variable that's been measured at an for example, we could have a variable measured at an interval level, but then find out that it wasn't normally distributed. We've already seen that when I was in the last lab, I did the total value of donations given. I think that that one was more or less normal. We've seen some, I've seen in some of your submitted assignments, which is fine, you weren't required to get a normally distributed variable. But many of you did encounter interval variables that were not normally distributed. And the issue there is that many of our calculations for interval level variables require use of the mean. And you can only do the mean and a standard deviation when you have a variable that's not only interval level, but also normally distributed. And so what's the point here? Well, that we often reclassify the values in a variable into a dichotomous outcome like this, 0 and 1s. So you could have, this could be an interval scale. We're talking about DICE, but to map this onto the social research you might be doing or the health research, this could be a scale. You know, I know the rate your pain scale usually goes from 1 to 10, but I'm sure you can imagine many rating scales. You might ask a patient, but for the purposes of certain research, it might only matter if a score was above or below 5, or it might only matter whether it was a 6 or not. And that's the case in this example. They're saying you win when you get 6s. So that's what matters. That's why 6 becomes a 1, and all the rest of these just get recoded into zeros in terms of their value in the box, because the statistical value or use of a number is not always dependent on the numbers, on the number as just a count. It might be a frequency or just be representative of a category. And so that's why we spend a little bit of time on thinking about the counting, and we'll look at this a little more in the review exercises. And we will get into observed values a bit later, so we can wait on that. These kittens are observed values because, see, like the standard error, they have chance in them, the white. Anyway, we will look at that more in a later lecture. What we really want to take home from this section is to remember that the observed value, the bit that we want to remember about this is that it's likely to be somewhere around the expected value. Like these ones, they're around the expected value, but off by a little bit. That little bit that it's off is the chance error, and we quantify chance error vis-a-vis the standard error. We can use the standard error as a tool because of other things we know about the distribution of variables. We can use our standard error to help us estimate probabilities using the normal curve. And this is a very useful tool that we will really explore more in Chapter 17 and again in next week's material. So we'll take a break here, and when we come back, we'll do some of the review exercises.